Hello, everyone. I would like to welcome you all to our joint webinar on design and optimization of screw machines in GT Suite using GT-SCORG. Let us wait for a minute or two to let all our attendees join in the Zoom session successfully. Great. So thank you everyone for joining in. A very good morning, good afternoon to all our attendees joining in from different time zones. I would like to welcome you all to this much awaited technical webinar on design and optimization of screw machines in GT Suite using GT-SCORG. My name is Atif Sheikh and I'm part of the GT marketing team. Today I will be your host for this webinar. We are thrilled and excited to have you all join us today. So before we get started, I'll quickly explain the flow of the webinar. This webinar is recorded and a link to the recording will be sent to you after the session. If you have any questions or doubts during the presentation, please type them into the Q&A box that you can see at the bottom, and we'll address them during the Q&A session at the end. This webinar will be total of 60 minutes, in which 45 minutes would be for the main presentation, followed by 15 minutes for the Q&A in the end. The Q&A session will be moderated by my colleague, Mr. Matteo Luzzi, and finally, we'll wrap up with some closing remarks. So now let's dive in today's joint webinar on design and optimization of screw machines in GT Suite using GT-SCORG. Can we have the next slide, please? Thank you. So I'm pleased to introduce our presenters for today, Mr. Doug Petrik from Gamma Technologies. Doug has been with Gamma Technologies for 2 years as a senior application engineer in the thermal fluids team. He specializes in positive displacement machines and lubricating systems. Doug has received his bachelor's degree in mechanical engineering from the University of Illinois at Urbana-Champaign. Prior to joining GT, he worked as a system planning engineer at Ameren for 3 years, where he focused on model development and simulation of natural gas transmission and distribution systems. We also have world-renowned screw machine expert, Professor Ahmed Kovacevic, director at PDM Analysis Limited. Professor Ahmed Kovacevic holds prestigious Royal Academy of Engineering Research Chair in Compressor Technology at City St. George University of London. His work is dedicated to developing of design excellence in academia and industry through research, teaching and collaborating with industry in numerical modeling analysis and design of positive displacement machines. He is the director of the for Compressor Technology and chairs international conferences on compressors and their systems. He is the director of PDM Analysis Limited, a spin-out company from Citi, which develops and commercializes SCORG. Professor Kovacevic has authored 11 books and book chapters, more than 200 reference journals and conference papers, several patents and industrial reports. He received 14 awards for his work, including prestigious IMEC James Clayton Prize in 2020, Institute of Measurement and Control Cornish Award in 2024, and J.N.E. Hall International Gold Medal in 2025. He is Fellow of Royal Academy of Engineering in the UK and Academician of the Research of the Academy of Science and Arts of Bosnia and Herzegovina. Without further ado, I will hand it over to Doug. Doug, the floor is yours.
Thank you, Atif, for the lovely introduction, and just wanted to say we're honored to have Professor Kovacevic here today. So, for the sake of time, I'll jump right into the webinar here, and here's an overview of the topics we'll cover today. So, if you haven't heard of GT Suite or SCORG before, we'll give an introduction on Gamma Technologies and the software, and Professor Kovacevic will give some insight on the screw machine industry and the software SCORG. Then we'll talk about GT-SCORG, which is a new feature that we've added into the software, and how you can use that for compressor multiphysics and system analysis. We'll talk about optimization, and we'll have some case studies along the way. And as a reminder, we do have a Q&A section at the end, so I encourage you to use the Q&A chat to ask any questions. It's being actively moderated by my colleague Matteo, so we'll answer those at the end of the session. So if you haven't heard of Gamma Technologies before, we are a company that develops simulation software, specifically multiphysics system simulation software. And so we're a little over 30 years old, and our headquarters is located in Chicago in the US, and that's where I'm located. But we also have offices globally in Europe as well as in Asia. In terms of the industries that we support, there's numerous industries ranging from automotive to off-highway and heavy equipment to aerospace, power generation, and HVAC/R. And so what is multiphysics system simulation software? So the idea of system simulation software is that you can bring in different multiphysics subsystems and model them all in one software to see how they interact. And we accomplish this by our multiple physics libraries, which ranges from flow and acoustics to thermal and mechanical libraries, as well as electric, electromagnetic, and chemistry. Controls as well, and even built-in 3D CFD and 3D FE capabilities, where the FE capabilities are primarily for thermal and structural uses. And so the software we make is called GT Suite, and it's more than just a solver. We have a post-processing environment, and we also have a pre-processing environment that we call Gem3D. And that's what this icon represents up here in the corner. And the goal of Gem3D is to enable you to build models faster directly from CAD. So what I mean is you can bring in CAD of, for example, a flow network, and automatically and easily build a 1D representation of that model and even animate it in 3D as a post-processing step. You can also use Gem3D for meshing of components for thermal or mechanical analysis. So maybe you've got some sort of heat exchanger or finned heat exchanger for a reciprocating compressor, or maybe a reed valve that you're studying the behavior of. So Gem3D enables you to do that quickly and easily with minimal expertise required in terms of meshing and model setup. So today we're going to talk about screw machines. But I want to point out that with our flow library and GT Suite, GT Suite's well suited for modeling any positive displacement machine if it can be represented as a chamber model. So that includes not just compressors such as scroll or expanders, but also liquid pumps such as gerotor pumps or vane pumps. In terms of the systems you can model in GT Suite, they're basically, if you can imagine it, we can model it. So that can range from air conditioning and refrigeration systems to air and process gases, oil, fuel, or other liquid systems, waste heat recovery, or even supercritical CO2. In terms of the fluids that are supported, we support pure gases, pure liquids, mixtures of gases and liquids, for example, a machine with oil injection, pure refrigerants, or even refrigerants in the two-phase regime using RefProp. And I just want to highlight, we're going to talk about GT Suite, and we'll introduce the new capabilities of GT-SCORG, but I want to highlight why even study screw machines in 1D. And it all goes back to the multiphysics. There's a lot of things that I could highlight here, but I want to point out just a few of them for the sake of time. For example, we may want to understand not just how the bare shaft compressor performs on its own, the thermodynamics and the bearings and the shaft, but maybe how it interacts with a system. We'll talk about that in more detail later today, but that's a key benefit of multiphysics system simulation for a screw machine. And being able to model the whole system and the surrounding systems enables you to study things like flow pulsations, NVH, that could potentially be addressed by things such as mufflers, resonators, silencers, or otherwise. And of course, modeling screw machines in 1D, the benefit of 1D simulation over something like 3D CFD or 3D FEA could give you some faster runtimes to study these systems and these subsystems together. So that enables you to do quick design iterations, get an idea for how things perform, and potentially reduce testing time and higher fidelity simulation time. So those are some of the key reasons why you may want to study a screw machine in 1D. And so with that, I'll hand it over to Professor Kovacevic to talk a little bit about PDM analysis and SCORG.
Thank you very much, Doug, for introduction, and also to Atif. I'm very pleased to have this to participate in this joint webinar of PDM analysis and GT gamma technologies. So let me just give you some information about where I come from and what PDM analysis and software SCORG are. So I've been in compressors for 40 years and 30 years, almost 30 years at City University, where we have a Center for Compressor Technology that was established in 1995. We have spun out a company called PDM Analysis Limited in 2014 to basically commercialize the research and software that we have developed from a research to compressor industry. So, and this is a software SCORG. And SCORG is, at the moment, we believe, industry-leading performance prediction software used for design, analysis, and optimization of rotary positive displacement machines. A part of the fact that SCORG provides operators and engineers with data-driven insight to design, which can be basically on their local machines. We have a solution online solution, which is called SCORG Alto, which is readily available and can be used in a case it is required by companies, and it allows very fast setup and always the latest version of SCORG with full security and in some cases reduced IT constraints. But let me tell you what SCORG is. Or first of all, why are we modeling these machines? Doug has mentioned a little bit about that, but what we want is accurate and fast performance prediction. We want, in some cases, to understand detailed flow patterns inside of the machine, to understand basically interaction between flow and solid deformations, because basically positive displacement machines work with very small clearances, and any change in temperatures or other conditions can be detrimental to a performance or reliability of these machines. But what I want to point out is that something like that already exists within SCORG, within GT, and maybe some other solvers. However, one unique requirement for these machines is analysis behavior of these machines in a system. And there are very few software which can do that. So that's exactly the idea why PDM analysis and gamma technologies put efforts together to form something, to form software which is called GT-SCORG, that will allow this seamless analysis of positive displacement screw machines in a system. Let me then just tell you what the SCORG is and how that implementation of GT-SCORG works. So SCORG is a comprehensive software that allows you full cycle of design and analysis of these machines, from rotor profile design and handling of profiles from CAD or other software, through calculation of volumes, ports, and other important elements, geometrical elements of a machine, so that that can be analyzed either by multi-chamber thermodynamics that exists in SCORG or within, for example, GT Suite. And we had that implementation before, as I will show in one of the next slides. But this also allows 3D grid generation in SCORG and interaction with any or most of existing CFD solvers. Moreover, when that is done, calculation of forces and boundary mappings can be done there so that the bearings can be selected inside of a SCORG, and then even full 3D design, 3D CAD design can be performed with Autodesk and some other solvers. And all of this is wrapped into what we call design exploration framework, so that you can analyze changes and determine what is the best configuration of machine for a particular use. And as you can see on the left-hand side of this slide, it works for twin screw machines, so compressors, expanders, pumps, IGSM, which are internally geared screw machines, that's the new type of machines, Roos blowers, gears, gear pumps, Vane, Quimby, and some other machines. So let me go step by step very quickly. So these are available rotor profiling capabilities of a SCORG, where we have this end rotor profile, which is our proprietary profile, which is, we believe, implemented in more than half of all new screw compressors built today. This is a family of profiles or a rotor profile generation methodology. But apart of that, we also have other profiles like pump profile, symmetric, asymmetric, equal, unequal, involute Roos blower profiles, internally geared screwed machine profiles, Quimby profiles, and obviously allow handling any CAD profiles in there. When designing a profile for screw machines, what is extremely important is clearance distribution of these profiles, especially in oil-injected screw machines, because in oil-injected screw machines, male rotor drives directly the female rotor. So the contact is extremely important in that case, because as you can see on a diagram on bottom left-hand side, depending on the position of a contact forces and sliding velocities are different. So the objective is to minimize both contact forces and sliding velocities, especially in new applications like water injected compressors or compressors with reduced viscosity lubricants. And that is done by clearance distribution, which is fully available in SCORG. Also in a SCORG, you can produce manufacturing tool or design a manufacturing tool for manufacturing of screw compressors. And these rotors are normally produced by either profile milling, grinding, or hobbing. So SCORG allows all of that. The second part, as I said, was geometry creation. And this slide here shows basically how the domains are broken so that they can be analyzed in using multi-chamber thermodynamics, which exists in SCORG. Once that is obtained, then full thermodynamic performance can be obtained in SCORG. Here are examples of P alpha, T alpha, mass alpha diagrams, force diagrams, torques on rotors, as well as representation of that on a 3D, which is used for exporting into finite element or CFD analysis. And based on all of that, you can then use the facilities in SCORG to design bearings, to select the bearings from a database that is existing in the SCORG, and requirements that you have for bearings, bearing life, and etc., etc. And also in the SCORG, as I said, we can directly interact with many CFD solvers to obtain simulations of single phase flows, like in oil-free compressors in here, or multi-phase flows like in oil-injected compressors, which example is given in here. And on top of that, you can go into full 3D parametric CAD design, where you can produce from a SCORG 3D CAD models, which could be then used for manufacturing, improved change, etc., fully parametrically. As it was said before, SCORG and GT Suite were integrated through the interface. So it is not directly integrated, but through the interface, where you could use this geometry calculation in a SCORG to run either multi-chamber thermodynamics of SCORG, or run GT suite thermodynamic calculations directly in a SCORG and produce results, or vice versa, use these results and import them into GT suite and then calculate the same performance in GT suite. So what we have done basically in this latest release is to integrate this machine setup and geometry generation together with the GT suite and create a new software which is called GT-SCORG that can be run directly from GT suite. So that's what I wanted to tell you. You can contact me on pdmanalysis.co.uk and we can discuss if there are any things that are required. So Doug, that's my part, and thank you very much for having me. So back to you.
Great. Thank you so much, Professor Kovacevic, for giving an overview of SCORG and a nice segue into what GT-SCORG is. So moving on, we'll talk a little bit about this new product that we've released in our latest version of GT Suite. So as Professor Kovacevic mentioned, and for anyone familiar with SCORG, some of the key inputs that you need to run a thermodynamic chamber model are, some geometry about the rotors, including these rotor profiles. Those are a key input. You then use these rotor profiles in SCORG, or historically you would have, to generate chamber volume and port area profiles and leakage area profiles. With our previous integration, you would then take these and run the thermodynamic calculation in GT Suite, either through the SCORG interface or in GT Suite itself. And so what GT-SCORG is if I highlight here, this part was basically SCORG's aspect, and this is where GT Suite was utilizing that. And then now with GT-SCORG, we've integrated both of those directly into the GT Suite interface. And so what I mean by that is we now have a subset of the SCORG capabilities, not the 3D mesh generation, but just the geometry calculations. So you can bring in your rotor profiles and your rotor geometry into GT Suite, into our user interface, and generate chamber volume, port area profiles, and even a GT model automatically. And so what that model you'll get will look like is what you see here. This is a chamber model representation where we have multiple chambers in the screw machine. You've got the suction flow, the discharge, and then all the colored lines between these chambers represent all the leakages, for example. So that could be blowhole leakages, that could be tip clearances, things of that nature. We also automatically include an oil injection port as well as an economizer or vapor injection, so you can model that in GT Suite as well. And so to show you what this new product within GT looks like, I'll give a quick demo here. So right now I'm in the GT Suite user interface, and we've added a new template here called SCORG Twin Screw Generator. And if you're familiar with the SCORG interface, you'll notice that there's a lot of overlap between the inputs that are required here. So you need to give us some information about the rotor geometry, for example, the distance between the rotor centers, the rotor length, etc. You also need to tell us what type of ports you have and when they open and close. And SCORG behind the scenes, included in GT Suite integrated in the software will calculate the profiles for you automatically. Of course, you also need the male and the female rotor profiles, so you can bring these in either just pasting in the data, or you can even use a file, for example. You could link to a text file or other format. And you can think of this template basically as kind of a generator or preprocessor. So you pick a directory where you'll output the model and the GT model, as well as an output for the name of the model. So for example, I've typed in example model here, and I'll run this live so that we can see what it looks like. But I also want to point out here in the options folder. So GT-SCORG, we've added this template into the GT Suite interface. GT-SCORG is one add-on license that you can use to generate these profiles. So for example, if you didn't have SCORG and you only needed volume and area profiles, you could reach out to Gamma Technologies to acquire a GT-SCORG license, which would enable you to use this function. But if you're an existing SCORG user, we do have compatibility with your existing SCORG installation. So all you need to do is point us to SCORG, and if you have an active license compatible with the geometry module of SCORG, you can use this functionality today. But I'll use GT-SCORG here. And if I run this model, we can see what happens. Actually, before I run it, I'll pull up a folder here to make it more clear what's going on. So this is a directory where I have this GT-SCORG model that we're looking at that has this generator. And there's nothing else in here. There was a folder I deleted, but if I go and I click run, this will call our solver, which will communicate with SCORG. Should only take a few moments, but what we'll see is that a folder is generated in here with that same name that I supplied. And we get a few things that I'll talk about in a moment. But if we go back to GT Post, which is our post-processing environment, I can come in here and go to the output, and we can see the rotor profiles that we brought in. So maybe I'll make this more square so we can look at it. These are the chamber volume and port areas that SCORG calculated behind the scenes, or GT-SCORG calculated. And we can look at, I like to filter some of these out to maybe the chamber volume and the port areas, so you can see the volume in red, the suction and discharge areas in blue and purple. But we also get all the leakage profiles. For example, if I turn off some of these plots here, we get all those leakage profiles, including the blowhole, the interlobe leakages, tip leakages, and face leakages. And you don't need to take this and copy, paste it, and bring it into another model. We can actually just go back to that folder that was generated. And you'll notice there's a few things that are important in here. One is that there's a GT model, a GTM file, called with that name that I supplied. There's also a few text files. One's called geom.gt and one's called GT parameters. And these are basically passing information from GT-SCORG to this GT model. So I can open this GT model by simply dragging and dropping it in the GT interface. And you'll see that we've already got a model set up for you here. The number of chambers that are in here depends on the number of lobes on your on the male rotor. So I used a 4-6 configuration. So we should have 4 times 3 chambers here per our convention. And all of those profiles, the chamber volume, the port area, and the leakage areas, those all come in on this part right here called screw shaft. If I go into our chamber geometry tab, you'll see there's a lot of green text here that represents different objects that are defined. So if I go into the chamber volume, for example, you'll see you get a preview of that chamber volume profile we were just looking at, and you'll notice that it's actually referencing that geom.gt text file. So all the information is automatically passed to this GT model, and if you wanted to pull it in automatically and make it, not reference the text file, that's easy to do in the interface as well. But the idea here is that it's automatically set up for you, so you don't need to do anything extra. So you can see all here's the blowhole leakage and the timing, the tip trailing leakage, the face leakages as well. And the entire model is linked up and connected for you. All you need to do is go to case setup and start supplying your boundary conditions. So that would be, pressures, temperatures, speed, if there's any oil injection, the pressure of the oil and the temperature of the oil along with the viscosity, and as well as maybe some geometry for the inlet and outlet piping. But you don't have to keep the model just how it is. You can build this out even further to incorporate other subsystems, which is really the main benefit of GT Suite for a screw machine. So just to summarize, GT-SCORG it has this new template in GT Suite. You have the ability to use a GT-SCORG add-on license or utilize your existing SCORG installation if you have a valid SCORG license. One other thing I want to show is, what kind of results would look like in this GT model. So I'll focus on just thermodynamics and flow, but we'll talk a little bit more about systems in a moment. So for example, I can come and click in GT Post after I run that model. I can come and look at pressures in the chamber, and you can see the pressure profile. I could look at a PV diagram if I want to evaluate the efficiency of the machine. Maybe I'm looking at temperature of the working gas. Maybe I want to see flow rates as well. So that would be at the outlet here, but I could come and click on this screw shaft, and it kind of brings a lot of the results that you might be interested in together. So things like the rotor speed, the fluid torque, fluid power, or even volumetric or mass flow rate as well. So here we can see what the mass flow rate pulsation looks like. You can also look at all the individual leakages. So for example, I could click on the blowhole leakage and see what that mass flow rate looks like. I actually have a report file that I can show here that kind of compiles that a little easier for us to look at. And so here you can see the chamber 1 volume and chamber 2. So they're at different points in the life cycle. This green line represents the blowhole leakage area between them. And we can see the blowhole leakage, the mass flow rate. It picks up when that port is open or when that leakage is open, and then when that leakage path is gone, that flow goes to 0. So of course the flow will be driven by the pressure difference between the chambers. And you can see how as the chamber 1 starts to compress, the flow rate of this leakage increases because there's a higher pressure differential between the two chambers. So these are just some of the thermodynamic results that you can get from GT Suite. So I'll go back to our slides here, and we'll talk a little bit more about compressor multiphysics and system analysis. So as we've kind of alluded to, it's common to analyze the compressor thermodynamics or the bare shaft compressor, but it's important to consider how it behaves with other subsystems. And it's important to optimize the machine for purposes of efficiency or even environmental impact. We all want machines to run more efficiently and cost less and be lighter on the environment, for example. And so it's important to optimize these machines in the context of the surrounding systems. So we've talked about the bare shaft compressor. That can include the shaft dynamics, bearings, seals, or even lubrication and oil injection. But in GT Suite, you could easily model a lubrication system that may have a pump, some oil separator, heat exchangers to cool the oil, and even a bearing solution that we have in GT to predict the oil consumption rate of the bearing. So you could use this to not only size the lubrication system, but see how it interacts due to the bearing loads from the compression process. Similarly, you might be interested in analyzing the shaft. You could analyze this in 1D, 2D, or 3D in GT Suite, including with an FE approach to see how those shaft dynamics may impact the screw machine operation or produce, NVH considerations. And within GT Suite, of course, that shaft is supported by bearings. So GT Suite has multiple bearing solutions. We have finite element bearings as well as mobility-based bearings. And I want to point out our finite element bearings are EHD capable as well, and also support oil refrigerant mixtures if that's something that is of concern. We also have a roller bearing solution, which is based off the SKF catalog that can be utilized. And maybe another system you might want to look at in GT Suite for this screw compressor is the inverter and motor in the drive unit. So my understanding is a lot of screw machines may be looking at or using variable frequency drives. So you can model that in GT Suite to see what that inverter looks like, that variable frequency drive, and what kind of three-phase output you'll get after that, and see how there might be some inverter motor interactions. Of course, in the motor, you might also be interested in the electromagnetics, so you could model that in GT Suite as well. Or you might be interested in the thermal side of the motor and take a look at that in GT Suite. And of course, if motors get hot, there's often a need to manage the temperature of it, so you can model the thermal management system, whatever that may look like, for the motor or other components within the screw machine. Now, talking a little, that was mostly kind of outside of the flow, But if we talk about the system that's driven by the screw compressor, we can talk about things like silencers or mufflers. So in GT Suite, you could model the muffler to see, or vary the muffler, even with parametric CAD, to see how that might affect the pulsations or the noise coming from the machine. And of course, there's many components in the downstream system that you could look at and see how the screw machine dynamics may impact that system. So that could be things like valve dynamics, heat exchangers, or even tanks and accumulators. So just looking at this picture here, we can see it's not just the compressor. The compressor is just one component in the overall system. In order to truly optimize these machines for the future of the compression industry, it's important to consider all the different subsystems and how they interact with one another, which is where GT Suite and our multi-physics capabilities can help you out. So I wanted to highlight a lovely case study on an integrated compressor model. And I'll point out that this is a scroll compressor application, but it's everything you see here is completely applicable to a screw machine as well. So Mercedes-Benz presented at Gamma Technologies Technical Conference a few years back, and they were looking to build a digital prototype for an electric refrigerant compressor for an electric vehicle application. And so they had a model of the scroll compressor positive displacement machine, a chamber model, as well as the two-phase circuit, including condensers and evaporator. They also had a mechanical model representing the shaft and the bearings, where the loads from the gas forces from the compressor were passed to the mechanical model. And they also had an electric machine driving the mechanical model and the overall compressor. And by building this model, they were able to analyze the startup procedure, so not a steady state, but a transient startup of the overall compressor. And you can see here in this plot at the top, there's a lot of noise in the blue line here for the shaft speed during startup. And that could produce some NVH concerns and maybe even be annoying to the passenger of this vehicle. So they were able to optimize the configuration of the shaft and the system to have a more reasonable response with less noise and a lower frequency response. They also did a measurement and compared it with the simulation. So here on the left was a measurement of the resonant frequencies, and here on the right is the simulated resonant frequencies, and you can see those align pretty well, illustrating the value of GT Suite and the capability of 1D simulation to predict those NVH considerations. So this was a great case study, and I challenge anyone in the audience to try to do something similar for a screw machine. I'd love to see what that looks like in that particular application. So I want to highlight a little bit of a few systems that maybe could be interesting for modeling the system interactions with the screw compressor. So here's an example of a heat pump system that you could model in GT Suite, including the condenser, evaporator, the expansion valves, and maybe an economizer with the heat exchanger. And of course, there may be vapor injection into the screw machine. So a detailed screw compressor model, for example, in GT Suite could easily account for vapor injection ports, and you can analyze how that affects the performance of the machine and the capabilities there. Another model or another system that may be suitable for analyzing a screw machine and understanding how the subsystems interact would be an electrolyzer system. So, during electrolysis, maybe H2O is used to, or water is used to produce O2 and H2, and the H2 or the hydrogen is used for something like a fuel cell or some other application. So you can model this electrolysis effect in GT Suite. And for example, maybe there's a screw compressor that compresses the H2 to a higher pressure for the downstream circuit or the downstream system. So you can model how the screw compressor interacts with this electrolysis system and see if there's any impacts due to the different subsystems and how that might affect the overall system. There could be ways to optimize the screw machine or even the system so that they're more compatible and produce better results. And taking it a step further, here's an example of a truck fuel cell system in GT Suite. So this is a very integrated system model with a hydrogen tank, fuel cells, cooling system, the battery, motor, inverter, the vehicle dynamics, and even controls. So maybe in the fuel cell, there's a screw machine that could be used to compress or boost the air. That would be a very interesting system where you could model the screw machine and see how that impacts the overall dynamics here. And another case where you might want to consider interactions with the overall system might just be multi-stage compression. So you might have two screw compressors or even different types of compressors that might interact with one another. So you could model both of these in GT Suite as easily as just bringing those two models of the screw machines together to study the performance impact, maybe transient behavior, or even NVH considerations due to the pulsations and interaction between the two compressors. So that was some examples of multi-physics and system analysis. I do want to talk, we've got a few minutes here to talk about optimization in GT Suite. So if you haven't used GT Suite before or you were unaware, we have an integrated design optimizer in GT Suite directly in the user interface. So you can set up all the factors you might want to optimize and the range or the values that may be suitable, as well as set up the responses and whatever your goal might be. So you may want to minimize leakages, minimize power consumption or noise and pulsations, and ultimately maybe you want to maximize performance. You could also put multiple responses here if you wanted to perform a multi-objective analysis and even do something like a Pareto optimization so you can see the trade-off between maybe efficiency and pulsation attenuation, for example. So maybe one example of an optimization workflow using GT-SCORG and GT Suite would look something like this. So I'll walk you through it real quick. Maybe you might have a parametric definition for the rotor profile, and you can use those parameters for the rotor profiles to generate those profiles. You could feed those into GT-SCORG to run the geometry calculation and create a GT model. You could then maybe use a Python script to set up the boundary conditions in that model, or even set up different cases, and then evaluate the performance of the machine at those operating conditions. So that's kind of what a normal workflow would look like, but you can easily integrate this with our design optimizer. So not only would you evaluate the performance, but then the optimizer will change the parameters to try and achieve whatever response or goal you have in mind. So you could run this automatically rather than having to do multiple iterations. So this could be an easy way to optimize rotor profiles or the overall compressor for some particular performance target. And of course, we've been talking about multi-physics and system analysis. So I want to point in that if you can imagine how these systems might fit into this process flow, you could easily incorporate subsystem models as well. So maybe there's model inputs to other subsystems like the HVAC arm system model, an electrolysis model, or maybe even the drive unit. So you could bring all of these together to evaluate performance and even run optimization not just on the rotor profiles, but the subsystems as well. So this would enable you to do complete system optimization, including the rotors, ports, subsystems, and you can do that all in GT Suite today. And to wrap things up before we get into the Q&A, and just a reminder, if you haven't been using the Q&A, feel free to ask any questions in there and we can address them. But just wanted to highlight a couple case studies. So here was a case study actually presented by my colleague Matteo here on the call at ICSM 2024 in Dortmund, Germany, where he analyzed the acoustic response of a screw machine. He used our parametric CAD capabilities in GEM 3D to basically change the shape and size of a silencer, generate a GT model of that silencer, and analyze how that affects or how well it can attenuate the pulsations, and then feed that into the design optimizer to then vary that parametric CAD. So you can see here on the right-hand side, Matteo was able to see the trade-off between efficiency and the attenuation of the pulsations. And you can see here the Pareto front, so you can see where there might be different designs and the trade-offs there. We can also look at this plot here and see the mass flow rate. So in red, this was with no silencer. There was a lot of pulsations, a high amplitude pulsation. But by optimizing the silencer design, you can see this green line right here is a pretty steady, almost constant flow rate. So that could be one way you could use GT Suite, for example, to optimize a silencer and reduce pulsations and NVH considerations. This is another example of a a case study published in the International Journal of Refrigeration, and it was a joint effort between Brunel University, London, and Howden. And here they modeled a two-phase twin screw expander for trilateral flash cycle applications. So this is an older case study where they used SCORG to generate the volume and area profiles, and then made a GT model of that and analyzed the performance of the expander with different inlet qualities. So you can see how the PV diagram here looks with different inlet qualities to the expander, and they looked into how that affected the overall isentropic efficiency of the machine, as well as the volumetric efficiency. And I'll point out here, different fluids could be studied as well beyond just the fluid they were looking at, that particular refrigerant. You can easily swap in different refrigerants and study those in GT Suite as well. So with that, thank you everyone for listening. We'll open it up to Q&A now. So I'd like to welcome my colleague Matteo here to share any interesting questions from the audience that we can address.
Hello, Doug. Thank you for the kind introduction, and greetings, everyone. Thank you for joining us today. Let me quickly introduce myself. I am Matteo Luzzi, and I am also a senior engineer in the thermal fluids team based in Stuttgart, Germany. I've been working at the company for almost 2.5 years now on the topics of detailed pumps and compressors and hydraulics in GT Suite. We had quite some interesting questions from the audience. Let us start with, and keep coming, thank you. Let us start with this one. First, to break the ice. The first question is relating to the optimization that we just mentioned. Does anyone interested into that need to use an extra license for that?
Yeah, so the design optimizer is built into GT Suite, so it's included with the GT Suite license. There's no additional license needed there. You do have control over how many solver licenses you use. So if you wanted to run, 16 parallel simulations, you would need 16 solver licenses. But otherwise, if you just wanted to perform optimization sequentially, that is something that's available with a GT Suite license.
Thank you. Another question from the audience. Can one use GT-SCORG on some form of pay-per-use basis online today?
Yeah, thanks for the question. So GT-SCORG is an add-on license, so it's not available today as a pay-per-use basis, on a pay-per-use basis. If you're interested in trying out GT-SCORG, we'd be happy to give you an opportunity to evaluate it, but unfortunately, it's not available in that format today.
Going on. Another question from the audience was, you mentioned that GT Suite can perform fluid structure interaction with screw compressors. Is this doable, and do you have any material as of today or plan to as of today?
Yeah, in terms of fluid structure interaction, I'd be interested to see the level of fidelity that you're interested in. In terms of, analyzing the shaft and bearings, we can easily pass the gas forces over to the shaft and transfer those loads. But if you're interested in like a detailed finite element FSI, unfortunately, we haven't done anything in that area yet. We've done that for scroll compressors. It's a new capability we have in GT Suite, but we'd be happy to look into this and further develop GT-SCORG in conjunction with PDM Analysis here to support a FSI workflow.
Right. Sorry for the slight detail. Moving on to a more
no problem.
setup question, interestingly. What would be a recommended computer configuration to be used ideally to run a full design optimization study like the ones highlighted here?
That's an interesting question, and I don't know if I'll be able to give you a fully satisfying answer, unfortunately. It ultimately depends on on the scale of the optimization that you're trying to accomplish. For example, that's something, with the fast runtime of a GT Suite model, which can be on the more order of minutes to hours, you may be able to do that with your regular PC, and depending on how many cores and licenses you have, you could split that up on all your cores. For full design optimization studies, we also have the capability for network distributed or local distributed if you have that available. So depending on what your use case is, you ultimately would probably want more cores so that you could run more iterations of that optimization loop. It also depends on the scope of the range of the input variables for that optimization. If it's a pretty wide range of inputs, it could be a longer optimization and would need more time and more cores. But if it's a more limited, like you're working within some constraints, that may be completely feasible today with just a typical work computer.
Thank you. Moving on to the next question. How well can the GT-SCORG system model fit into a digital twin development?
That's a really interesting question. I think it should be able to fit in relatively easily because within GT Suite, we have a machine learning assistant, for example, that could be used for developing a digital twin of a twin screw compressor. So GT-SCORG could be utilized to, ultimately, the first step is always to start with a physics-based model, typically. So you would use GT-SCORG to create that detailed screw compressor model, run that, and then from there, the goal is typically to build a meta model, usually a neural network-based meta model for that. We have an interesting case study where we actually used, for a reciprocating compressor, we performed fault detection using a machine learning algorithm that could simulate and predict. We simulated and then predicted faults for that reciprocating compressor, and I could see GT-SCORG being useful for that first step, building out the compressor model to do something like that.
Thank you. Thank you for organizing such an interesting webinar. Oil-injected compressors are quite challenging in terms of modeling the effects of oil mixing on heat exchange and leakage flow in one dimension. What is your experience on the topic?
That's a really good question as well, and you're completely correct. It is a challenging problem. In terms of GT Suite, we have multiple leakage models ranging from simple orifice solutions to something like Couette-Poiseuille flow, for example, for rectangular channels. These are 1D solutions, and we do have what we call a homogeneous mixture model. So if there's detailed underlying, fluid dynamics due to the two phases in that leakage gap, that's certainly something that could require calibration for a system model. We'd be interested to implement any specific models that are, if there's anything in the literature that would represent those leakage flows adequately, we'd be happy to implement those in GT Suite for higher accuracy.
All right. I've been having quite some interesting questions in general.
Yeah, these are great questions.
Being lagging a bit behind here by just mere quantity. Would using GT Suite for analyzing friction effect of the contact between rotary vanes and rotor housing possible?
So with this, I presume this is rotary, like the lobes of the screw machine for this question. I'm not sure by vanes. When I hear vane, I usually think of like a rolling piston or a vane style compressor. In terms of the friction effect there, it could be a little tricky to model depending on the lubrication of it. But in GT Suite, we have a generalized contact model that potentially could be utilized. I didn't have a slide here today, but for example, you can have contact between two surfaces coming together, and whether it's 2D or 3D. So we don't have any work illustrating that today, but if you're interested in that, we'd be happy to look into that and investigate.
Can I comment on this
Of course,
question?
Professor Kovacevic.
Few previous questions. So within SCORG, there is that model that I've shown, which allows you to make a clearance distribution and analyze the forces, so contact forces and sliding velocities. So that is readily available in SCORG, and it can be done. Also, when we are talking about fluid-solid interaction and CFD simulation or finite element simulation, so SCORG, maybe not GT-SCORG, but SCORG allows you to, so gives boundary and initial conditions for such a calculation. And with the 3D models that we have, it is possible to be done. Obviously, it can be integrated in the GT suite later on, but it depends on interest and requirements.
Great, thanks for the detailed additional information, Professor Kovacevic.
All right, let us have another quick technical question in here. Nice example on the acoustics. Damping in a screw machine. Do you have capabilities to model both reactive and absorptive silencers there?
You know, Matteo, you're the expert on that publication. You want to answer?
Yeah, the short answer is yes, it can be done. What you see right now on screen was the absorptive silencer, which is using a very thick wool-like material to damp pressure oscillations coming from the machine. But of course, more basic formulations like having a number of tuned chambers and baffles in there with perforated tubes and channels to create resonating chambers to dampen at need, like Helmholtz resonators, like to dampen the pressure pulsations in the same measure, but without the need of this such material, can be analyzed as well. Both kind of geometries are fully handled in Gen 3D as of today.
Thanks, Matteo.
You're welcome.
I know we've got a few minutes left here.
We may close with another question, if
Sure.
if I may.
Go ahead.
We know that yearly Professor Kovacevic organizes and hosts a very renowned conference in London. Are you planning to participate to that event as well? And if so, can you share any future work that you may be publishing there?
Yeah, good question. Yeah, and that actually segues perfectly into kind of what we were going to show here at the end. So of course, yeah, the upcoming 14th International Conference on Compressors and Their Systems is coming up this September. And I'd like to highlight that we have Gamma Technologies has several publications that we'll be sharing there related to scroll compressor bearing design, multi-physics modeling, including structural, thermal deformation, elastro-hydrodynamic thrust bearings, and leakage predictions, as well as a more system-focused model where we're investigating the acoustic response of a CO2 heat pump system. So these are some of the publications we'll have there, and I encourage everyone come and meet us in September. We'd love to talk with you. And additionally, for the short course that will be the weekend before the conference, so that's I believe September 6th and 7th, Matteo will be giving a session here on GT Suite 1D and quasi 3D modeling for detailed compressor modeling. So it probably won't be just screw machines. It'll focus on other compressors as well. But we encourage you to come and meet us there. And I guess, Professor Kovacevic, anything you'd like to add about the conference? I think you're muted, Professor Kovacevic.
Yes, we are welcoming all others in the conference. So thank you very much for pointing that out. We have a very interesting program scheduled, and do welcome. Do join us. We are welcome.
Great. And with that, I think, if you liked what you saw today and you want to learn more, feel free to reach out to us via our websites. You can contact us directly through the Gamma Technologies page or PDM Analysis. Their contact information is there, and you can reach out and talk with Professor Kovacevic. If you want to reach out to me specifically, there's my email as well. I'd be happy to answer any questions and learn more about the systems that you guys are modeling.
Great. Thanks, Doug, and thank you, Professor. I think with that, Doug, I think in the interest of time, I think we can close the session. With that, I would like to thank everyone, all the attendees, for allocating their time and joining us today for this interesting webinar. If you have any additional questions, you can email us directly to Doug. And thank you very much. Have a good day, everyone. Thank you. And yeah, thank you.